Hello, Calculus 3 students. We're talking about cross products today. It's from section 12.4. Cross product is an extension of the dot product, where the dot product was just a scalar. What we're going to get from the cross product is we're going to get a vector quantity. That means that this vector is going to have both a magnitude and it's going to have a direction. So you'll note when I try to find the magnitude of the cross product, this is what I'm going to be doing. I'm going to be, and this is a definition, so this is what we're given. We are defining what the cross product is, and it is the magnitude of u times the magnitude of v times the sine of the angle in between those two, where the direction is given by the right-hand rule. And you'll see a picture over here where they're saying what you do is you curl your fingers from U to V, and the direction of your thumb would be the direction of that cross product. Now, what you can note is that this direction is always going to be orthogonal to both this U, V. So here we just have another picture of a vector u, v with the cross product and showing that direction just tilted in real space. The geometry of the cross product, if the two cross products are parallel, then so if the vectors are both parallel, then the cross product is going to be 0. Note that the sine of 0 degrees, because there's 0 degrees in between them, is 0, and of course that would make sense. We're also stating that, if you'll note, this makes a parallelogram, and the magnitude of that the magnitude of that cross product is the area of that parallelogram. So let's look at what we have here if we're going to find the magnitude and direction of u cross v. We're not really going to find the exact direction. We'll cover that in just a few moments later on in the video. We're just going to say that it is, when you do the right hand rule here, and when you cross your fingers from U to V, your thumb projects out in this direction of this green arrow here. So let's just go ahead and find the magnitude of the cross product. We've already discussed the direction, and I'm just going to write down this formula here, and then I'm going to plug in. Just plugging in these quantities, and then we need to know the angle in between these two. Note that this is the I and the J direction. It is basically a 45-degree triangle with it, because each of these quantities is a 1 in both the I and J direction. So what you're going to get is a 45-degree in between there. The Z value actually just tilts it in space. So it's going to be the sine of 45 degrees. And then whatever I get from there. Alright, and then that answer is 2. So the magnitude of that u cross v is 2, and it is in this direction here, orthogonal to both u and v. Let's take a look at a few of the properties of the cross product. Of special interest is this property here, because it really depends on which direction that you start, whether it's u cross v or v cross u, as to how you twirl your hand. If it's u cross v, your fingers go from u to v. If it's v cross u, your fingers go in the opposite direction, which is from v to u. So what happens is we get this, what's called an anti-commutative property. So it just means that it's in the opposite direction. The scalars here factor out, so for the associative property that's pretty straightforward, and distributive property is also straightforward. What's of interest is this commutative property, because it is called an anti-commutative property. Now when I look at example 2, they're wanting me to compute the cross product of unit vectors. Basically they're wanting me to look at the next theorem, which this will follow from. If I look at each of the unit vectors, notice that they are mutually orthogonal, meaning that they are 90 degrees from each other. That would mean that the angle in between them is pi over 2. If I look at any one of the magnitudes of I, then I would note that each of the magnitudes is just going to be 1. So I'll mark that down. So that's very handy. So if I were to do, let's say I cross j, then I would do magnitude of I, magnitude of j, times the sine of pi over 2. Notice that this is then going to be just a 1, a magnitude of 1 in the direction of k. Therefore, I can say that I cross j is that unit vector k. And it follows from that, if I keep going through here and I say j cross I, would then be, oops, I don't want to do j cross I yet. It's going to be negative k. I'll just go ahead and do it because it's going to be negative k due to the anti-commutative property, and so I'll just go ahead and do j cross k. It's going to be very similar. J cross k is then going to be I, and the opposite is going to be the negative I. So I'm going to write those down. So here's the cross product of all of the different unit vectors, and they just equal the other unit vector in whichever direction. So you've basically derived this theorem 12.5 here, and which is really pretty. Well, you didn't really do the I cross I, but the angle between I and I is 0 degrees, so the sine of that would be easy enough to just write down. The sine of 0 degrees is 0, so of course these cross products would be 0, a unit vector composed on itself. I guess I should have done that one. I can do it. Yeah, we won't do that. Alright, we'll go on to the next. The next theorem allows me to get the actual values for both the magnitude and direction of this cross product. What I need to do, and this is the proof of the theorem above, is I note that each u vector and v vector, if I'm going to cross those two, I write down the cross product here, and I note that it's going to be the multiplication of that u and v quantity of those components of the I, and the u and the v of that I and j. And I notice that this carries on all the way through here if I were to work it completely out. And it looks very messy because the whole thing is this wad of stuff right here. But if you'll notice carefully, it just happens to be the determinant of each of these matrices here, which is very convenient. So that means when I do the cross product, a nice easy way to do it is you write down all of the values of each component, and then you would do the cross product of each of those. Well, they asked me to find the area of a triangle with those particular vertices, so I am going to use the cross product to get that. What I'll do is note that it is this that could be extended so that I could say that it's a parallelogram, and at the very beginning, if we remember back, we said the geometry of the cross product was that if u and v are two sides of a parallelogram, then their area was that cross product. Alright, so we're going to use that fact to get the area of this triangle. Of course, it'd probably be easier just to do it directly, but we're going to use cross product and get that answer. If I say that I'm looking at vector OP crossed with vector OQ, then what I'll need to do is use my formula above, and I'm going to put my I, J, K components here. Going to be, so I'm going to need to write down each of these components, and I'm going to have to do the I components, J and K components. That would be 2 minus 0, write that down, 3 minus 0, and 4 minus 0. Then for the OQ vector, it's 3 minus the 0, 2 minus the 0, I'm glad they had it at 0, and then 0 minus 0 made that easy on me. I would like the cross product between these two vectors. What I'm going to need to do is I need the determinant of this matrix. If you remember back from matrices, knock out this column, and it's 3, 4, 2, 0, multiplied by I. Oops, it's plus minus plus. Remember the plus minus plus deal, so that one needs to be a minus. So write minus and knock out the J column. 2, 4, 3, 0, J hat. Alright, I've completed that. I just took the value of each of these and wrote them out here to the side. Next, I need the magnitude of this cross product, and this will be the area of that parallelogram. I don't really want that. I want that divided by 2 so that I can get the area of the triangle. I'll do that. Alright, in doing that arithmetic, I get about 7.63. On to the next one. In this next example, they want me to find a vector that is normal to the following two vectors, or orthogonal. If it's normal, then it's orthogonal. All I need to do is just find the cross product of these two vectors, and I'm going to have a vector that is orthogonal. I'm going to use my theorem that I did before, where I just find the determinant of this matrix and write in all of the values for u. Let's see, I is minus 1, j we don't have 1, k is 6, 2, minus 5, minus 3, then find the determinant of that. Doing that computation on the determinant, I get this vector here, and this vector would be orthogonal to the two vectors uv. Pretty straightforward on that one. In this example, they're defining torque to be the cross product of that arm length, the magnitude of that arm length, times the magnitude of the force, times the sine of the angle in between them. So that's going to be our definition for torque. In our example, they ask us to do this twice. However, they tell me that the magnitude of my first wrench, the magnitude of that arm length is 0.15. The magnitude of the force is 20 newtons, and the angle in between those two is 60 degrees. So for torque, the magnitude of that torque, you're just going to it'll be the cross product, but we're already given everything in terms of magnitude, so it makes it pretty nice. It's just going to be the 0.15 times the 20 times the sine of 60 degrees. Same thing over here. They've given us the magnitude of that arm length, the magnitude of the force, and the angle in between. Just straight plug and chug as far as this is concerned. 0.25 times the 20 times the sine of 135. They've already crunched those numbers for us, and they tell us that this torque would be 3.5 Newton meters, and this one would be the 2.6 Newton meters. So the B wrench is the winner of which one would apply more torque. The next problem that we're going to do is magnetic force on a moving charge. If you look at the animation that the book provides for this one, you'll get to watch this little charge move all the way around the circle here and watch how the vectors themselves, they look as they go around this circle. It's very cool. They ask me first up for the force. In A, they want the magnitude and direction of the force, and they tell me that that is given by, and they're going to tell you your formulas. You're not expected to know these formulas or have them memorized or anything of that sort. They'll tell them to you. Oops. So they give me the formula for this. So I know that this force vector equals Q times the cross product of vector V and vector B. Now the key in this problem is noting that B is the magnetic field and B is going to be in that direction of negative K. So vector B is actually equal to the unit vector, negative K. Alright, so I take my Q, 1.6 times 10 to the minus 19, and then I'm going to multiply that by the cross product of vector V and B, and you'll note here that in order to get that magnitude, it's just going to be the magnitude of V times the magnitude of B. I want the entire vector, so I'm just going to look at it as vector, where's V? V is 9.0 times 10, well, it wasn't a 0, but I wrote it in anyway, and that happens to be in that I direction. And then I'm going to cross it with the negative K vector. And because these are all in different directions and they are 90 degrees apart, then you will have the sign of that 90 degrees. I and K are 90 degrees apart, and the sign of that 90 will then be 1 if you were to do this using the right hand rule. A vector between that is crossed I to K and will end up being that J vector. So I get 1.44, and that follows from that right hand rule and those properties that we looked at earlier in that other example. So that would be your force vector. This R, they give me the formula for this, rewriting for B, R would be equal to the mass times the magnitude of velocity, the velocity vector squared, times the magnitude of the force vector. That's nice because it's just in that direction, so it is just that number. Same with the velocity, except for that he's squared, so I'll just write all those in. Alright, and there we have it. There's the radius of that proton doing the number crunching, and and because these are all 90 degrees from each other, it makes it very nice, and the problem kind of falls out nicely. Alright, if you have any questions, see me in the Collaborate.